Hello everybody. All right, welcome back. Let's dig into the Evo former. What we saw in the last session is that basically um, this network takes in an input. Where's the network? Yeah, it takes in the input sequence. Let's see. Yeah, takes in the input sequence and then finds two kinds of features. It does a database search, pairwise features, and also finds the multiple sequence alignments. And based on these two sources of data, it combines them, sends them both into the Evo format, the real neural network here, and based on that, it directly predicts the 3D positions of each amino acid in 3D space, basically, right? That's how it gets the positioning, uh, and then it keeps sending it back through the network multiple passes to keep iteratively improving on its prediction over time. Okay, so today we went through all this in the last session, right, in the last live stream, and finally we get to this, the Evo former, right? Alright, let's read it together. So the key principle of the Evo former is to view the prediction of protein structures as a graph inference problem. Yeah, so we already saw what a graph inference problem is, right? Basically, a graph inference problem in 3D space means that you are trying to estimate the properties of a graph based on whatever information you have, right? And the graphs here are basically the carbon atoms or the amino acids that act as the beads of the necklace, right? In which the edges of the graphs are defined by residues in proximity. Okay, residue proximity. Let's see what that means. Residue in proximity. The edges of the graphs are defined by residues in proximity. I use DenseWiki, which is a tool that you can download if you use this link. For example, go to densewiki.org and you should be able to download this tool that I'm using here. You can also join the Discord for dense readers. But anyway, let's get back to it now. So residue proximity is crucial in understanding how proteins work. Proteins work as following a complex way. The function of a protein often depends on the specific combination. Okay. So if you take a linear, protein, where's this sequence? Here's what's going on. So you take this linear protein input sequence, and now you need to figure out how to twist and turn this long string into a 3D structure, right? And so by turning it into a graph inference problem, you're trying to see which beads here are connected through a like a weak bond, basically a weak electrostatic bond, which is what these residue proximity means. This in itself could be considered to be a graph, right? A 3D graph with many nodes and many connections between it, right? So that's the format that this network is trying to. That's how it sees the problem of converting it into a graph. Okay. The elements of the paired representation encode information about the relationship between. Okay, there's the paired information representation, right? We saw that we gave two types of data to the model, and one of them was the paired representation. And then there's the MSA representation. Those in which the sequences in which the residues appear. Let's see what's going on here. I don't know what that means. MSA column. Okay. You know what MSA is, right? An MSA arranges multiple protein or DNA sequences to highlight regions of similarity. Okay. Each column, MSA columns are the vertical stacks of aligned characters. So it's like arranging multiple DNA sequences side by side to highlight similarity. Okay. Okay. The sequences. Maybe that's a better query for this. Rows represent sequences. Never mind. Within this network framework, we define a number of update operations that apply to each block, in which the different update operations are applied in series. Okay, so this is this is where we're really going deep into what uh, what the MSA actually looks like, right? Three A. Okay, let's look at 3A. 3A is okay. I get the MSA representation, right? These are the columns and the pair representation. Pair with bias, column wise gets itself. Hmm. Pair representation, it looks like this. It looks like a graph, right? Again, is interpreted as directed edges in a graph. Okay, triangle multiplicative update and triangle self-attention. Let's see what this is. Okay, so there's triangle self-attention and multiplicative update, right? Let's look into both of these. It is a clever trick used in protein structure. Okay, especially with deep learning models like AlphaFold. Okay, think of a protein as a complex chain. You want to know the distance between any 2 points. Imagine points A, B, and C. You directly predict in B, C using neural network. A, B, and C. The predictive distance AC is consistent with the other two. Hmm. I guess the last part is the main one, which is like basically you're trying to make sure that it enforces some geometric constraints, some sanity checks on its own predictions of positioning. Okay, self-attention helps the model understand how different parts of protein interact with each other. If two amino acids are both near a third, they themselves are likely to be in proximity. Okay, makes sense. This allows the model to infer more relationships. Richer picture. Oh, okay, okay, I see. Okay, so the circles represent residues. Fair enough. Then D is structure prediction module, including invariant point attention (IMBA) modeling. Invariant point attention module. Okay, I haven't seen that, gotten to that part yet. The MSA representation updates the pair representation through an element-wise outer product. Pair representation encodes the relationship between every pair of amino acid. It's a grid where each row and cell represent an amino acid. Mm. Pair representation as inputs to learn the intricate rules that govern protein folding. Okay, sorry, we are back. Yeah, so the MSA representation updates the pair representation to an element-wise outer product dimension. Okay, I don't need to. I think this is not very. I don't need to go into all these details of exactly how the model would train. Applied within every block, in contrast to parameter, applied within every block. Rather than once in a network. Let's look at this one again. This diagram. I think this is what. And I keep coming back to it, right? So the pair representation yeah, it's keeps improve going back to the pair representation, right? So I guess it makes sense that the MSA improves the the evolving MSA representation. Okay. Consistency of the pair representation. For a pairwise description of amino acids to be representable as a reasonable 3D structure, many constraints must be satisfied. Okay, on the basis of intuition, we arrange the update operations in terms of triangles of edges, extra logic bias to actual retention. Let's see what this means. Logic bias. Adding a constant value to the logic, pre-sigmoid. And because input along with different axes. Axial retention is a clever trick using machine learning, especially with grid level data. Okay. Okay, first applies attention along one axis, each row and then each column. Mm, okay, this is interesting. Interesting. Similar to how we read one line at a time, then move down the page. Extra logic bias to axial attention. Okay, what was the logic bias?
Hi guys,
Okay.
guys, you guys can hear me? Okay, so let's start. My name is Francisco, and I'm going to be talking about open-ended conversational chatbots today with you guys. Uh, and I'm going to be focusing on the Japanese section.
That was for
So a little bit about us, about my company and me. And I'm sorry if the levels are the levels are really really small. It's probably the gamma that I always get. About sleep, you can see how dark is very big on my T-shirt. We are focusing on training
Hmm.
programs, mostly focused
Anyway,
on
I think I'm
research
getting a little sleepy now,
for
so I will
engineers originally, and now also
cut
for
here. You know,
non-engineers.
it's very soon,
We actually
but
study research
let's end here today.
with a
I'll come
mostly
back to it
physical
later. Yep.
background. So